Hey there, welcome back. I am glad to be here, and I think I'm feeling a little better than I was last recording, so hopefully my voice holds out. Anywho, we are starting a new chapter. We're looking at chapter 4 in this current textbook, and in whatever chapter number it is, it's rational functions and graphs and rational equations, all kinds of fun stuff with rationals. And you might notice that my first slide, it says 4.2, and I'm going to actually later be in 4.1. I'm going a little bit out of order in this current book because I feel like it makes more sense this way. So don't worry, you still are going to be responsible for both sections. Okay, so what are we doing? We're looking at rational functions first, and then we're going to look at how to graph them. And then later, we'll look at solving the equations in the future recording. So what is a rational function? Rational function is a function of the form f of x equals p of x over q of x. Okay, so what that means is you got this function where you have a polynomial over a polynomial. You've got a fraction. And that's exactly what rational means. You know, if a number is a rational number, it can be written as a fraction. So a function that's rational can be written as a fraction, but specifically the numerator and denominator are polynomials. And you always have to make sure the denominator isn't 0. So the q of x, or that bottom polynomial, is not supposed to equal 0, because then you have something that's undefined, and you can't work with that. So, and you're going to see when we graph that the graph has something special going on in those places where what would make the bottom 0. Like there's something special going on there. Okay, so yeah, a rational function is really just a ratio or fraction. And just like I just said, fractions can't have 0 in the denominator. And two, just like other fractions you've worked with, sometimes you need to reduce to lowest terms. And we'll be working with the special case of that, where we have to simplify the fraction first, and then go ahead and graph the result. But we still have to be really careful and keep in mind that the denominator at any time cannot be 0. All right, so what's that special thing going on? Well, in those places where the denominator could be 0, where the denominator would be 0, that ends up being something special called a vertical asymptote when we go to graph it. It's an invisible vertical line the graph won't cross. And in other features of the graph, other features of the function, you can have something called a horizontal asymptote. That's a invisible horizontal line that the graph may or may not cross, but it at least gives you an idea of the pattern of the graph, even if the graph crosses it. And then you can also have something called an oblique asymptote, which we're not going to get into in this course, but an oblique asymptote is still an invisible line that the graph may or may not cross. So we're just going to worry about the vertical and horizontal asymptotes. And for the purposes of this course, we're not going to get into depth with them. We're just going to use some summarized steps and how to find the asymptotes and how to graph them. If you want to really get into depth, stick around in math, and eventually in calculus you'll get into depth about the asymptotes. Okay, so vertical asymptotes. Invisible vertical lines, and the graph will never cross those. The denominator cannot be 0. The graph will not cross those vertical lines. They lie at places that would make the denominator 0. Okay, for example, let's see here. Let's say you have a function like f of x equals x minus 5 over x plus 3. Okay, this x minus 5 can't be factored, x plus 3 can't be factored, this can't be simplified. Something to keep in mind though, as we're going to work with it, we know that x plus 3 cannot be 0. That'll make the denominator of the fraction 0. So x can't be negative 3. So x equals negative 3 is a vertical asymptote. So when you go to graph the function, I'm not going to graph the whole function right now, but when you do go to graph it, at x equals -3, you draw yourself like a dashed vertical line. And dashed in the graph tells people that, okay, it's kind of there, but it's invisible. It's like a little invisible fence. And what's going to happen when you graph is that the graph is never going to touch or cross this vertical line. So that's something called a vertical asymptote. And again, that's not the entire graph, but that at least shows you the asymptote. Horizontal asymptotes, they are invisible horizontal lines that the graphs of rational functions may or may not cross. But even if the graph does cross them, it gives you a good, it's kind of like a little fence that you can hop over. It gives you kind of a feel for a path the graph should take generally, even if the graph crosses over it. Now for us, finding the horizontal asymptotes, we're going to do this in a quick summarized way. We're going to look at the degree of the numerator, degree of the denominator, and then the leading coefficients of each of the numerator and denominator, and we're going to use those to help us determine if there's horizontal asymptotes and what types, where they would be. Okay, but real quickly, what is the degree of a polynomial? Just to review that real quickly. When a polynomial is written with the variables in alphabetical order and the exponents in descending order, the degree is the number of the highest exponent, or if there's several variables, it's the sum of the exponents on that for leading term. And the leading coefficient is the coefficient of the first term listed on the left. Okay, so let's say you have a polynomial like 7x to the 5th plus 8x cubed minus 3. Let's say you have something like that. This is in descending order because the exponents count down 5 to 3 to 0. And then the highest exponent is 5. So the degree of that term of 7x to the 5th is 5. Degree of the polynomial is that 5 also. And then the leading coefficient is the coefficient of that first term, and that's the 7. Okay, so we're going to be examining those two pieces of information and using those to help us to figure out horizontal asymptotes. Okay, so to find the horizontal asymptotes, if any exist, first look at the degree of the numerator and the degree of the denominator. And this is where we're just doing a shortcut, shortcut from calculus. If the degrees are the same, then the horizontal asymptote is y equals the ratio of the leading coefficients. If the degree is less than the degree of the denominator, then the horizontal asymptote is y equals 0. And if the degree of the numerator is greater, then there is no horizontal asymptote. It is possible to have something called an oblique asymptote if the degree on the numerator is 1 higher than the degree in the denominator, but we will not be finding and graphing those. We're not going to worry about those right now, but those are a possibility as well. All right, so let's look at a couple of examples of just finding horizontal asymptotes. Okay, so same problem I mentioned a few minutes ago. We had f of x equals x minus 5 over x plus 3. We already found the vertical asymptote, x equals -3. But keep in mind, with x minus 5, that's like x to the first minus 5. The degree is 1. Leading coefficient is also 1. And for x plus 3, degree is 1. Leading coefficient is also 1. So since the degrees are the same, for your horizontal asymptote, it's a horizontal line, so it's going to be y equals, it's going to be the ratio of those leading coefficients. So the top leading coefficient over the bottom leading coefficient. So 1 over 1, which is 1. So y equals 1 is the horizontal asymptote for that particular graph. Like that. Now, it's not the entire graph, again, because you do have that vertical asymptote, plus you have, other points and things and curves and stuff you need to graph, but just showing you that horizontal asymptote. So the graphs may or may not cross this line, but it's going to follow along a path close to that line. So that'll be part of your graphing process. Okay, next scenario was, what if the exponent in the numerator is smaller than the exponent in the denominator? Like, let's say you have f of x, the degree, let's say f of x equals x over 4 minus x squared. Which you could write that also as f of x equals x over negative x squared plus 4. Getting those polynomials in descending order. Okay, so for the numerator, your degree is 1. Your leading coefficient is 1. For the denominator, your degree is 2. So you're looking at your leading exponent, and your leading coefficient is negative 1. So in this case, since the degree in the numerator is less than the degree in the denominator, your horizontal asymptote is going to be y equals 0. So automatically, if that happens, if the degree in the numerator is smaller than the degree in the denominator, you just have y equals 0. And so you've got that horizontal line. It's basically the x-axis. I'm kind of drawing it slightly above the x-axis so you can see it, but it is the x-axis, y equals 0. So there it goes. Okay, and third scenario. Let's say we have something like f of x equals 2x squared plus 3 over x minus 4. Okay, so for 2x squared plus 3, the degree is 2, leading coefficient is 2, and for x minus 4, degree is 1, leading coefficient is 1. The degree here is higher in the numerator than it is in the denominator, so there is no horizontal asymptote. In this particular case, there is no oblique asymptote because your degree in the numerator is 1 higher than the degree in the denominator. To find the oblique asymptote, you would have to do some long division. Divide 2x squared plus 3 by x minus 4, and then whatever your quotient is, ignoring the remainder, that would be your horizontal asymptote. Again, you're not responsible for that right now, but just wanted to give you that FYI that that problem does have a horizontal asymptote, or a oblique asymptote. I keep saying horizontal. It does have an oblique asymptote, it's not a horizontal one. Okay, next. Let's take this a little further. Let's finish graphing these things. After you've taken care of vertical asymptotes, horizontal asymptotes, and in the future oblique asymptotes, find and graph your y-intercepts, find and graph your x-intercepts. That'll give you some points to work with. Then find some additional points. Make sure you have at least 3 points on each side of the vertical asymptote, if not more. So you're probably going to need more in order to get a real idea of the curve, the shape. And then when you're done getting enough points, connect the points with smooth curves, remembering you never cross the vertical asymptotes. Okay, so back to the first problem I had thrown up there. Back when we were talking about vertical asymptotes. F of x equals x minus 5 over x plus 3. We already know the vertical asymptote is at x equals -3. We already know the horizontal asymptote was y equals 1. We know all that from earlier, from doing this problem earlier, so nothing new there. Okay, let's find our x-intercepts. Wherever it crosses the x-axis, y is 0. So we got to figure out where x minus 5 over x plus 3 equals 0. Well, in order to equal 0, the numerator has to be 0. 0 divided by some number is 0. So where's x minus 5 equals 0? It's at x equals 5. So 5 comma 0 is an x-intercept. So it's right there. And then for y-intercepts, where it crosses y-axis, x is 0. So evaluate f at 0. So you got 0 minus 5 over 0 plus 3. So that's -5/3. So we have a y-intercept at 0 comma -5/3. Or -1 2/3, which is right here. Then get some more points. These 2 points aren't nearly enough to know what this graph's supposed to look like. So let's try plugging in -1 and -2 on this side to get a little bit better idea. And also let's plug in +2. So that'll give us a better idea about this curve. Maybe let's try plugging in 8, or let's do 9. Okay, so if I plug in -1, I'm going to get -6/2, which is -3. If I plug in -2, I'm going to get -7/1, which is -7. If I plug in 2, I'm going to get -3/5. If I plug in 9, I'm going to get 4/12, or 1/3. Okay. So -1, -3, -2, -7, 2, -3/5, 9, 1/3. That's 9, 1, 2, 3, 4, 6, 7, 8, 9. Yeah. Okay, so those points at least give me an idea what's happening to the right of my vertical asymptote. I have this nice little curve. Notice as it goes down, it's going to get closer and closer to your vertical asymptote, but it's not actually going to cross it. And as it goes up and to the right, it's going to get closer and closer to the horizontal asymptote, but it's actually not going to cross it. So the horizontal asymptote in this case is something that's not going to cross, but it also shows you the trend, like the pattern of where the graph's going. Now that's not the whole graph though. You still have some to the left of the vertical asymptote you got to worry about. So since I'm running out of space, let me do a new XY table right here. Let's put in 1, 2, 3. Let's put in -4, -5, 3, 4, 5, 6, 7, 8, 9, -9. Maybe that'll give you an idea about that side. So if I plug in -4, I'm going to get -9 over -1, so I'm going to get 9. If I plug in -5, I'm going to get -10 over -2, which is 5. If I plug in -9, I'm going to get -14 over -6, which is going to be 7/3. Let's see if that gives me enough. 7/3 is the same thing as 2 1/3. Okay. Then we get a curve that's similar to this one, except it's going like this. You know, and I could get more points if I want to get a nicer shape to the curve, but since I'm kind of familiar with how these go, I don't really need to. But it's going to be another curve. It's going to go like that. So, you know, as it goes up, it's going to get closer and closer to your vertical asymptote, but it's not going to cross it. And as it goes to the left, it's going to get closer and closer to your horizontal asymptote, but it's not going to cross it. So there you go. So there's graphing and with the vertical asymptote and horizontal asymptote. You make sure you get your asymptotes, your intercepts, and then at least 3 points on each side of your vertical asymptote, if not more. And that's how you graph it by hand. Okay, skip on to here. You can graph using your TI-83. Just make sure you're aware that the calculator is kind of wonky. If you have an older model, it might try to connect parts of the graph where your vertical asymptotes are. Might not always give you the best picture. Let's see here. Let's pull up my calculator. Let's do it. Y equals, let's put in x minus 5 over x plus 3. It's important to put your numerator and denominator in parentheses because your calculator does follow order of operations. Oh, I had a window left over from a previous experience, so let me change this. Oops, sorry. Let's go to Zoom and let's do number 6, Z standard. That'll give me my -10 to 10 type screen. Oh, so this time it worked out all right. It didn't do it wrong. All right, you see the curve? You see the curve. That's exactly what we got. The same graph. Vertical asymptote here, invisible vertical line. Sometimes your calculator will try to connect dots here. Just be aware of that. So you might see some weird zig line here. Not always, but just be aware. So that's why it is still important that you know what's going on with the asymptotes and so forth. But your calculators can graph those for you. Okay. And another interesting case, graphs with holes. Sometimes you'll find you have a rational function that has a fraction that needs to be reduced. Before reducing, write down what values of x are not allowed. In other words, what would normally cause the bottom to be 0. Do that before reducing the fraction. Graph the result, and then leave a hole at the point where that x value needed to be excluded. Okay, let me show you. Let's say you have something like f of x equals x squared minus 16 over x plus 4. Okay, right off the bat, we know x plus 4 cannot be 0. So we know that x cannot equal -4. But then we try to work with this a little further. X squared minus 16 can be factored, and the numerator ends up having a common factor with the denominator. So this can be reduced. When we go to graph, we're going to graph the reduced form of the function. What you're going to notice is a line. F of x equals x minus 4. That's the equation of a line in slope-intercept form. But since this is truly a rational function when we started, we can graph that line, but we got to make sure we leave a hole where x is -4. We have to leave that value out. It's not part of the domain of the original function. So x equals 4 has y-intercept at 0, -4, has a slope of 1, so 1 over 1, 1 over 1. Or we could go backwards, down 1, left 1, down 1, left 1. But when we get to x equals -4, there we leave a hole. Then that's your graph of your rational function. You just have to make sure to leave that hole there. Ta-da! If you do it on your calculator, let's do that function on your calculator. Don't put in the reduced form. Put in the original function. Put in x squared minus 16 divided by x plus 4. And hit graph. And right now it's going to look pretty normal. It's like, oh, that just looks like a line. Notice that the hole isn't visible right now. You're going to have to zoom in to see the hole. So we're going to, let's do this. Let's just, let's change our window. Let's change x min to be -6. Let's change x max to be -2. Let's change y min. Let's see, because the hole is at what? -4, 1, 2, -8. So let's leave y min at -10. Let's change y max to -6. And let's hit graph. And now we see it. Look right here. You can see that gap. It's tiny, but you can see it. And if you want to see it even better, change your window even more. Change it to maybe -5 to -1 and maybe -9 to, or up here, not -1. Change that to -3 and then change that -9 and -7. Let's do that. You'll see it even more. So there's your hole right there. So you wouldn't be able to see it until you zoomed in, but you'd have to know to zoom in. So you have to know what's going on with the function. You can't just rely on your calculator. I know. It's so sad, isn't it? All right. Let's look at two specific rational functions. This is going to have us jetting back to 4.1. So this is where we're going to go slightly backwards. 4.1, they introduced these two specific rational functions, and I'd rather talk about rational functions in general first before doing this, so that's why I go out of order. But anyways, you got a specific one called the reciprocal function, f of x equals 1 over x, and then you've got another one, f of x equals 1 over x squared. You can find that a lot of times you're dealing with rational functions of these two types. And if you go into your book, page 271, there's a nice function capsule for f of x equals 1 over x. F of x equals 1 over x. The denominator is x equals 0. At x equals 0 is a vertical asymptote. Numerator has a degree of 0. Denominator has a degree of 1. So numerator has a smaller degree than denominator. So our horizontal asymptote is at y equals 0. Then you start plotting some points. There is no x-intercept, there is no y-intercept for this particular function. Notice, what the curves look like. It's decreasing as you go from -infinity towards 0, and it's decreasing as you go from 0 to positive infinity. Discontinuous there, we're at x equals 0. It is an odd function. This graph is symmetric with respect to the origin. Okay, and what are you going to have to be able to do? You're going to have to be able to do some graphing. So let's see here. Let's say you have something like f of x equals 1 over x minus 1 plus 1. All right, so what do you have here? Well, if you wanted to graph it the other way, the manual way that we were just doing, it would help to have this all combined into one rational function. So let's do this. Change 1 into x over x, or x minus 1 over x minus 1. So f of x equals x over x minus 1. Let's see, vertical asymptote, x minus 1 equals 0, so x equals 1. Horizontal asymptote, degree of the numerator is 1, degree of the denominator is 1, leading coefficients are 1, so it's y equals 1. All right, x-intercepts. Where does x over x minus 1 equals 0? It equals it at x equals 0, so 0, comma 0. And then y-intercepts, f at 0 is 0 over 0 minus 1, so 0. So 0, comma 0. All right, so x equals 1. As our vertical asymptote. Y equals 1 as our horizontal asymptote. We got 0, 0. Need some more points. Let's plug in 2, 3, and 6. So 2 over 1 is 2. 3 over 2 or 3 halves. 6 over 5. So 2 comma 2. 3 comma 1.5. 6 comma 1 and 1/5. So we get an idea of the location of the curve. And then to the left, let's see, we got 0, 0. Let's plug in -1, and let's plug in -7. All right, -1 over -2, so 1/2. -7 over -8, so 7/8. So yeah, you're getting an idea of where that curve is. All right, now remember, going back to our book, f of x equals 1 over x looks like this. Vertical asymptote at x equals 0, horizontal asymptote at y equals 0. What we have here has the same looking curve, just shifted. But if you look back at the original function looks like the 1 over x function. Check it out. If let's say you start with f of x equals 1 over x. As soon as you say f of x equals 1 over x minus 1, this minus 1 subtracting from the x means you're shifting to the right 1 unit. So you took the whole graph and shifted it to the right. So your vertical asymptote now is at x equals 1. These curves are now each shifted over 1 to the right. Then as soon as you add 1 to the whole thing, you're shifting up 1. So where you had before you had the horizontal asymptote at y equals 0, you now have it at y equals 1. All of your points are shifted up 1. So you can either use the way I talked about earlier to graph, where you find all your asymptotes, find your intercepts, find some points, or if it fits one of these two forms, use your rules of shifting, stretching, reflecting, shrinking, etc. to get your graph. So there's two ways to do it, and it's up to you which way you do it. Okay, let's do one more of those. F of x equals -2 over x minus 3 squared. Okay, well, let's go back to the book for a second. This page, this page after that. F of x equals 1 over x squared. That's another rational function they talk about in 4.1. Looks like this. As you're going from left to right, it's increasing as you approach 0, and it's decreasing as you keep going to the right away from 0. X equals 0 is a vertical asymptote, y equals 0 is a horizontal asymptote. This one's even, this function, is symmetric with respect to the y-axis. So what we're getting ready to graph here has that x squared on the bottom. Notice we subtract 3 from the x, so that tells us we're going to be shifting to the right 3. Notice that we've multiplied by 2, so that's a stretch by a factor of 2. And we've also negated the whole thing, which means we're going to have a reflection across our x-axis. So I know all those things, and I can apply all those things if I really want to the graphing it, or I can use the techniques I learned earlier. Okay. Let's see, for the vertical asymptote, x minus 3 squared, that would have to equal 0. So x would have to be 3. Horizontal asymptote is going to be y equals 0. I can tell that right away because there's no x in the numerator, but there's x squared down in the denominator. And the degree of the numerator is smaller than the degree of the denominator, so automatically that gives us y equals 0 for our horizontal asymptote. So x equals 3 for the vertical. And y equals 0 for the horizontal. It's actually the x-axis, but I'll kind of draw it a little offset so you can kind of see it there. Okay, let's see. All right, so there we go. X-intercepts. Where does it cross the x-axis? Y is 0. There is none because numerator is never going to be 0. Okay, y-intercept. We're going to find f at 0. So we've got -2 over 0 minus 3 squared. So that's -2 over -3 times -3, or 9. So -2/9. So it's right here. Close enough. It's hard to do those fractions. All right, I need more points. So xy. Hey, if I get the left side, I can reflect and do the right side. Remember this. The original function f of x equals 1 over x squared is symmetric about the y-axis. Well, technically it's symmetric about the vertical asymptote. So wherever your vertical asymptote is, you can get your left side and reflect across to get the right side, or vice versa, right, reflect to left. But anyways, let's put in 1 and 2. Let's see if I put in 1, -2 over -2 times -2 is 4. -2 over 4, which is -1/2. Right here. If I put in 2, -2 over 1 is -2. It just confirms what I know already about the way this curve is supposed to look. And it's just going to keep getting closer and closer to that vertical asymptote there. And I should be able to reflect across and get the same things. So at 6, -2 over 6 minus 3 is 3. 3 squared is 9. So I get -2 over 9 again, which is expected. Remember our y-intercept was at -2 ninths. Well, 1, 2, 3 over is at -2 ninths. 1, 2, 3 over is again at -2 ninths. Plug in 5, I should get -1/2. 5 minus 3 is 2, squared is 4, -2 fourths. Yep, I do. So that's right here. If I plug in 4, I should get -2. And I do. So that's right there. Okay. So yes, this satisfies exactly what I was talking about there. It takes the 1 over x squared graph, x minus 3, shifts it to the right 3. 1, 2, 3. So now your vertical asymptote is at x equals 3. The multiplying by 2 stretches it by a factor of 2, kind of stretches it out. And then the next multiplying by -2 also reflects it across your x-axis there. So instead of being up here, it's down here. It's reflected. So there you go. So that's graphing one of that form. Okay. Well, I hope that's enough showing you how to do this by hand. I would like to punch those into the calculator real quickly just to show you again how to do that and how it looks. Keep. Okay, so just real quickly, let's punch into the calculator. Let's punch in f of x equals 1 over x minus 1. Very careful to keep things grouped properly. Don't want this to get messed up. And then when I hit graph, it's still on the old window, so I'm not going to see much. So let me go to zoom and let me get this squared up, standardized. There's the graph. It was shifted right 1 and up 1. There it is. Or the second one I just did. Let's see, -2 divided by, and then it was x minus 3 squared. You should be able to hit graph. And there it is. It's shifted over 3 units. So here's your vertical asymptote, and it's reflected across the x-axis, and it's stretched by that factor of 2. So now you can see it. All right. Well, thank you for joining us. That was your introduction to rational functions and graphs. Make sure you practice, practice, practice. You have a lot to make sure you're able to do here. And next time you join us, we're going to be solving equations, rational equations. It's going to be so much fun. Have equal signs and find x, all that good stuff. All right. Take care. Thank you.